All right. Trig.
Yay.
And as usual, we're going to start with some painfully basic stuff and grow. Lecture 1.7. Trigonometric functions. Okay, again, if you're all upset with something I've done, just let me know. Otherwise, I'll keep staring at the board. Okay. Okay, we're going to talk about why we need these. We're going to talk about angles. We're going to define them. We're going to talk about the properties. We're going to show graphs, somehow magically in an hour. We're going to find some special values, and we're going to do some examples. Okay, so first, why do we need trig functions? Or why do we need periodic functions generally? To model things that recur, okay, at regular intervals, okay? Things that are circular or cyclic, recurring or periodic, okay? For example, orbits, or things that go roundy round in general. Things that bounce up and down. Things like the tide, sunrise, weather, okay? Things, physiological things, like, let's say, heartbeats, breathing, circadian rhythms. Music and sound. Sound's a wave, and images contain frequencies. So in both of those, you'll see things that are, let's say, frequency methods, and we'll talk about some of that. And light, okay? Or any kind of wave, which oscillates in both position and time. So obviously we need periodic functions. And we're going to talk about a special family of periodic functions, which are the trigonometric functions. Okay, before I do that, a few examples. This is the kind of stuff I was staring at for ages during my master's. These are simulated physiological waveforms. And you can see that there's periodic stuff going on. Let's say periodic. There's the oscillations going on, say, the time scale of a heartbeat or less. Then there's some stuff going on the scale of a breath or less. And this is actually simulating a sick person. Someone whose control system is screwed up in such a way that the breathing envelope does this. It oscillates as well. In such a way that for some time, this person isn't breathing. And those are called apneas. Okay, so this is meant to model something called central sleep apnea. That's one example. Second example. I stole this off of a Bill Nye video, so there's a link there to that. This is a really cool thing. When you're looking for planets outside our solar system, you often can't see the planet, but what you can do is you can see its effect on a star. Okay, so a star that has a planet going around it wobbles. And this is showing that wobble. So you measure the star's motion, and this is called the radial velocity method. You measure the star's wobble, and from that you can infer that it's got a planet going around it. And in fact, for this guy, not only is it waving in one way, it's also waving in another way, suggesting it's got two planets going around it. Okay? So again, oscillating stuff and models. And this is a very successful and sort of, I think, the first method for finding planets outside our solar system. Finally. Will you run? Okay. On the left is the real thing, or a model of the real thing, and on the right is obviously a computer simulation. This predicts tides, okay? This is a machine with pulleys and cranks, and you turn the crank, and it traces out on this piece of paper, or over there, the expected tide, okay? And you can imagine that predicting the tide would be important for naval things, okay? For instance, in the D-Day landing, it was important. And this is difficult to do by hand, and it's error-prone to do by hand. But before computers, this is what they did. They built these big, beautiful machines to do it, to predict the tides. And this essentially involves combining a bunch of sinusoids in an intelligent way. Okay? And to figure out how to set this thing up, they have to have a different kind of machine for analysis of these things. So you analyze the tide using one machine, and then you can simulate the tides like this. Okay? Big, beautiful machines. Okay? Any questions so far? And this is the 1800s, 1900s, and as far as I'm concerned, it's just amazing that you can do this. Any questions at all? Okay, the real stuff. Okay, what we're going to talk about, we're going to talk about the unit circle. Okay, circle of radius 1. That's 1, that's 1. And we're going to talk about a point P that's going around the circle. And before I forget to say this, like the exponentials and the logarithmic functions, the trig functions are transcendental, okay? You can't evaluate a trig function generally with a finite number of algebraic operations, if that matters to you, okay? So you can't just punch in square root x minus 1 over 2 and expect that to give you like the sine of something, okay? They're not that kind of function. Okay, so let's talk about angles. Okay, you can measure these in degrees, which is a fairly crappy way to measure them, okay? In a full circle, there's 360 degrees, okay? But again, that's a weird way to measure things. So there's a more natural way to measure things, which is the radian. So the natural measure of angles is the radian. Okay, and unless you're told otherwise, everything is in radians, okay? So have your calculators in radian mode, have your brains in radian mode, unless someone tells you otherwise. And again, this is kind of like the base E when we talk about exponentials and logarithms. This is the natural sort of unit that we work in when we talk about trig functions. Okay, the definition of the radian measure of an angle. Suppose you have a sector, or like a pie slice of a circle, okay? You've got an angle here, this is the radius of the circle, and this is what's called the arc length. Okay? The radian measure of that angle is given by the arc length over the radius. Okay? And these are both in units of length, and so this whole thing is unitless. Okay? So you can write rad after it, but really it's unitless. It's got no dimensions at all. And in particular, if you've got a pie slice that looks like that, where the arc length is r, you'll see that that is 1 radian. Okay? Okay, and I said in a full circle, oh no, don't worry about the degrees yet. In a full circle, okay, the arc length is just the circumference of the circle, so 2 pi r. 2 pi r over r gives you 2 pi. So there's 2 pi radians in a full circle. Okay? 360 degrees, 2 pi radians. Okay, so for example, if I ask you how many radians or how many degrees are there in a quarter turn of a circle, you should be able to figure that out. If we give you something in radians, you should be able to convert it to degrees, and from degrees to radians. For example, if I say convert 135 degrees to radians, what I was taught to do was to take it and multiply it by a converting factor. Okay, in 180 degrees, there are pi radians. Okay, and if I write it like this, then the degrees will cancel out and I'll be left with a unitless radian. Okay? Or you could write 2 pi over 360 because of this, if that makes you happier. Okay? Anyway, so what I did was multiply by a conversion factor to cancel out the degrees, leaving me with unitless radians. And I believe that's 3/4 pi. Yeah. 3/4 pi. Okay? And I know some people, for these kinds of unit conversions, you like to write sort of an equation with 2 ratios and an x in there, and you solve for x. If you want to do that, you can do that. Okay? Questions? So, silence. Okay. All right, back to this guy. And screw up your notes a bit. We associate with the point an angle measured in a standard way. Okay? So again, this radius was 1. Okay, and we measure angles like this, counterclockwise from the positive x-axis. Okay? So if the point was here, the angle would be 0. We increase through positive angles going this way, or if we measured this way, then we decrease through negative angles. Okay? For example, again, assume all these circles are unit circles, unless I say otherwise. Okay, if we want to talk about, this is another example. If we want to talk about minus 7/4 pi radians, The minus says we have to go this way, clockwise. And you wind up here. Okay? You wind up in the same place as if you'd done theta equals pi over 4 radians. Okay? But you got there going the other way. Questions? Again, positive angles are swept out this way, negative angles are swept out clockwise. Any questions? Okay. Sine and cosine functions. Okay. For any real number theta, define the sine of theta, denoted sin theta, as the y-coordinate of the point P as just described over there. Okay? So for this guy here, that would be the sine. Okay? That. The cosine of theta, cos theta, as the x-coordinate of P. Again, measured in that standard way. Good? So for example, incredibly boring table with some sines and cosines that we can figure out quite quickly. So for example, let's look at 0. Okay, when theta is 0, the point is here. The x-coordinate is 1, so the cosine is 1, and the y-coordinate is 0, so the sine is 0. At minus pi over 2, the x-coordinate is 0, so the cosine is 0, and the y-coordinate is minus 1, so the sine is minus 1. Does that make sense? Okay. And that's just a table of stuff like that, okay, which we can get by going order turns around the circle in either direction. All right, from this definition, you can see that the domain of sine and cosine, so the domain for both, someone want to tell me? Everything? Good. Okay, so the domain is everything, okay? Whatever number I can put in there, yeah, I can turn that much and find out the sine and cosine. And the range? How's this? Okay, minus 1 to 1. Okay? However much I go around this circle, the x-coordinate and the y-coordinate are bounded by minus 1 and 1. Okay? And I span that whole interval. Does that make sense? Okay, so the range is from minus 1 to 1. Okay. Some properties of these guys. And for a lot of you, I appreciate that this is very, very review. And for those it isn't, don't worry. Okay. The sine and cosine functions are 2 pi periodic, or they're periodic with a fundamental period of 2 pi. And there's the version there for any number theta and any integer n. If you add an integer multiple of 2 pi to theta, you wind up with the same sign, and same deal with the cosine. Okay? Or thinking about another way, if you add or subtract 2 pi from an angle, you wind up with the same sign and cosine. Okay, why? If I go 2 pi radians around, I wind up at the same place, so the same sine and cosine. The other way, same deal. Same for any any integer multiple of 2 pi. Does that make sense? You wind up in the same place, so you get the same sine and cosine. The sine function is odd. Okay? So, for example, if instead of turning this way, I turn this way by, let's pretend that was the same amount. Okay? The y-coordinate is negated, which is all that says. Sine function is odd. Okay? And that's true for any theta. The cosine function is even. So again, if I turn the other way, the x-coordinate is the same in both cases. So the cosine doesn't change, so the cosine is even. Okay? And finally, the Pythagorean identity. What did we have here? We had, and again, for any theta this works. I keep sticking in the first quadrant. Okay, this bit is sine theta. This bit is cosine theta. And by Pythagoras, okay, and the radius of the circle was 1. And by Pythagoras, you can see that if you square this, add it to the square of this, you'll get 1 squared or 1. Okay? And for general theta that works, you can use what's called the distance formula, or just think about it. If you go over here, the distance of a point P is obtained by the distance squared is equal to the distance from the origin is equal to the x-coordinate squared plus the y-coordinate squared, square root all of it, and that'll give you the same result. Any questions about that? Yes, ma'am?
Can you re-explain this circle? The sine function is odd, the sine function is
Okay, so if you go this way a certain amount, okay, then you'll get some sign, which is how high up you are. If you go the other way, the same amount, you'll be below by that amount. Okay? Above, below by the same amount. That's why that happens.
Okay, yeah, because like y theta is like sine of theta, like
Yes, that's right.
always
Yeah,
on
yeah.
the word
Yeah, y is sine. Yeah, that's right.
Okay, and x is
Cos.
sine.
And you're here. And that'll happen for any theta. Okay, and again, you can either use, forgive me, the Pythagorean theorem to figure this out, or the distance formula, or whatever, okay, to see the Pythagorean identity. Okay, and I realize I'm talking quickly. I'm assuming this makes sense to you anyway. Does it make sense, or does anyone have any questions? Okay. And look at this funny notation. We wrote sine squared theta when we meant sine of theta squared. Right? So remember that for the trig functions. This is weird notation. It's inconsistent with a number of things. It's inconsistent with how we talk about inverses, right? Inverses aren't reciprocals. And this is inconsistent with that. But do remember this. When we write sine squared or cos squared or whatever, we're saying take the function and square it. Okay? If you have a question, shout, please. Okay, we're not at the graph yet. Okay, again, we can't evaluate these functions exactly in general, but for some special values we can evaluate them exactly using special triangles. Some special triangles. Here's one of them. It's an isosceles right triangle. Okay, so these angles are both 45 degrees, or pi over 4. Okay? And if I give these lengths, length 1, 1 squared plus 1 squared, square root that, you've got square root 2. Good? And if you want, you can think of this instead as the similar triangle, where again you've got pi over 4 and pi over 4, but you've scaled everything down, so this guy's unit length, and you've got 1 over root 2 and 1 over root 2. Okay? Another special triangle. I said isosceles, right? Not equilateral. This is an equilateral triangle. 60 degrees, 60 degrees, 60 degrees. Okay? Or pi over 3. If I drop this perpendicular down, I get pi over 6 up here, and I get a right angle here. Okay? Suppose this equilateral triangle had side length 2. So that would be 2, that would be 2, and each of those would be 1. Okay? By Pythagoras, this side length is the square root of 2 squared minus 1 squared, or the square root of 3. Okay, so that's our second special triangle. pi over 3, right angle, pi over 6, 2, 1, root 3. Which is similar to, if you like, pi over 3, or 60 degrees, pi over 6, or 30 degrees, and scale everything down. Okay? One moment, please. No questions? Yes? Say that one more time, please. This one, pi over 4 radians, or 45 degrees. Yes?
Could you just possibly make the triangles like this?
I could, couldn't I?
Yeah,
Yes.
thank you.
In future, yes, thank you. Okay. I'll refer you to video this time. That's okay. Or the internet. Do you have any questions about this right now or no? No? I'll pretend you answered whatever. Okay. So let's do an example, and I'm going to do a somewhat weirdish example. Okay, for example, let's find sine and cosine for minus 4/3 pi. Great big frequency. Okay, again, everything's going to be a unit circle unless I tell you otherwise. That's x, that's y. Okay, minus, so go clockwise from the positive x-axis. Minus 4/3 pi. We wind up here-ish. Okay, so that's pi, and that's another third of pi. Okay, so this guy here is pi over 3. Pi over 3. Okay? All right, then I draw a triangle in here. All right, and again, the radius of the circle is 1. And I say, hey, would you look at that? It looks like this guy. Okay? Or you could have started with this guy and used similar triangles to get there. Okay, so I can label this now. This is 1/2. That was 1. This is root 3 over 2. Good? Okay? Now I'd like to label this as minus 1/2 to tell me that this x-coordinate is negative, and this is plus root 3 over 2 to tell me that this y-coordinate is positive. Okay? And then from that I can just write that the cosine of that angle theta is minus 1/2, and the sine of that angle theta is positive root 3 over 2. Okay? And if you really wanted to, you could use those sort of even odd things to say that the cosine of this guy is the same as the cosine of just 4/3 pi. And you could use the oddness of sine to do that, if that makes your life better. Okay? But be able to do something like this. Does this make sense? Yes, ma'am.
Do we have to answer the plus?
Do you have to say again?
Yeah, do we?
No, no, I just wanted to, for exciting emphasis. Okay? Graphs of the sine and cosine functions. Which, let me tell you, were a pleasure to produce. Okay? These are the values of sine and cosine corresponding to those special triangles. Sometimes I'll write things like 1 over square root 2 as square root 2 over 2. Okay, those are the same. Okay, if you know about rationalizing the denominator. Okay, if you multiply top and bottom by root 2, you get this. Similar thing for 1 over root 3. Okay, so if you see those, they're the same. Every space between vertical, this is a nice effect we got here. Okay, yeah, every space between vertical grid lines here is pi over 12. Okay? And so you can just check that things that make sense with those special triangles and the unit circle will make sense here. Okay? That's sine, that's cos. Okay? If you have any questions about this, I'm happy to answer them. Special points. Again, the special values are labeled there, so just have a look at a few of them and make sure that they make sense to you. Note where these guys are 0, right? The sine is 0 at any integer times pi. Okay? The cosine is 0 at pi over 2, then pi over 2 plus 2 pi, then pi over 2 plus 4 pi, and so on. And also pi over 2. Take that back. The cosine function is 0 at pi over 2, then pi over 2 plus pi, then pi over 2 plus 2 pi, and so on. And pi over 2 minus pi, pi over 2 minus 2 pi, pi over 2 minus 3 pi, and so on. Okay? So again, zeros of sine are at k times pi, k an integer, and zeros of cosine are at pi over 2 plus pi times k, k an integer. Does that make sense? Okay. Domain and range, we talked about already, right? The domain is everything for both of them. The range for both of them is from -1 to 1. The period, what's the period of each one? We already said it. 2 pi, good. What else? Even, odd. This guy's odd. If I turn it around 180 degrees, I get the same thing. This guy's even. If I flip him over like that, it's the same thing. And notice that if I shift this guy pi over 2 to the left, I get this guy. They're exactly the same shape, just shifted with respect to one another. Okay? Questions? Yes, ma'am.
Can you please go over the example you did right there? Yeah.
Okay. I saw that minus. That tells me to go clockwise from the positive x-axis. 4/3 pi. Pi is 180 degrees, you can think of it that way. Okay, and what's left to turn is 1/3 pi. So that's 1/3 pi. Okay, that lands me here. The radius of my unit circle is 1, and I can see this guy over there. So I just copy those numbers over. I see that this x-coordinate has to be negative, so I write -1/2 to avoid confusing myself. That y-coordinate is obviously positive, so I write plus √3/2, and then I just read off the x and y coordinates and write them as a sine and cosine.
Thank you.
Thank you. Okay? All right. And again, in case I mumbled this, I'm just going to say this one more time. The distance of a point xy from the origin, okay, is given by this. Okay, so you can use that for the Pythagorean identity. Okay? Aight. The tangent function. Tangent function. Okay, if you like pictures, and this is almost completely useless. If you like pictures, again, unit circle, point P, that's theta. Okay, if I draw a tangent to the circle at P and extend it to the x-axis, okay, that length, and this is why it's called the tangent, that length is the size of the tangent at theta. Okay? And that's true everywhere. You can prove using similar triangles. You can just look it up or try it out or ask me if you want to know how. The tangent of theta, okay, so that size is the same size as this, again by similar triangles. Sine over cos. Okay? And so we define tan theta as equal to sine theta over cos theta. Okay, and the reason we're saying that is what? If I had a point here and I just said this length is tan and this length is tan, tan would always just be a non-negative number. Okay? So to give it a sign as well, we define it consistently like this. Does that make sense? So this is a sine and a size now. Okay, notice that if theta is 0, the tangent is nothing, so tan of 0 is 0. If I go over here, or how about this? If I approach here, right, the tangent goes out and gets longer and longer and longer and longer and longer. So it blows up. And over here, it never hits the x-axis. So at pi over 2, the tangent is undefined. And similarly, it's not defined pi over 2, minus pi over 2, or 2 pi n plus either of those. Okay? Graph time. Okay, that's the graph of the tangent function, which I've shown you before, and you've probably seen before. Again, these values are associated with the special triangles again. You can check a few of them out if you want. The grid line separation is the same as it was before. And again, notice that tan 0 is equal to 0. Tan pi is equal to 0, as you can see from the picture as well, and so on. And so the zeros are at k times pi, k an integer. Okay? These asymptotes, what do they correspond to? Again, plus minus pi over 2, plus minus 3 pi over 2, plus minus 5 pi over 2, and so on. Okay? They're everywhere where this tangent goes away and never touches the x-axis. Okay? Vertical asymptotes, where the tan function is undefined. Questions yet? Okay, what's the domain of that thing? Almost everything? Right. And almost is actually a mathematical word, which is fine. Okay, so let's see what the domain of this is. The domain is almost everything. All x such as x is not pi over 2 plus k pi, k an integer. Okay? So this thing doesn't work at pi over 2, it doesn't work at pi over 2 plus pi, pi over 2 plus 2 pi, pi over 2 minus pi, pi over 2 minus 2 pi, and so on. Okay? I put up a graph of the tangent function and I put some red lines in there. Those are not part of the function, okay? Those are the asymptotes, the tan is not defined there. And the range? Everything. Yeah? Goes there. Okay? Period? Pi, not 2 pi, it's pi, yeah? It's repeating every pi. Period is pi. And it's odd. If I turn this 180 degrees, I get the same thing. And you can prove that using these guys as well. Questions? Yes, ma'am.
What's the range for cos function?
Say it one more time, please.
What's the range for cosine function?
The range?
For cosine.
The range for sine and cosine is minus 1 to 1, including both.
Same for cosine.
Yeah, sine and cosine look exactly the same, they're just shifted this way. Good? Alright. And again, just so I've said this, the zeros of this guy. Are at integer multiples of pi. Zero, pi, 2 pi, and so on. Okay? Okay, again, I'm just going to repeat the zeros of the sine and cosine functions. Okay, sine theta is 0 at integer multiples of pi. Cos theta is 0 at pi over 2 plus integer multiples of pi. Okay? And tan is sine over cos. So tan is 0 at the same place as sine is 0, and tan is undefined at the same place as the cos is 0. Okay? Okay. For acute angles, okay, the ones that are between 0 and pi over 2, we can think of theta as an angle in a right triangle like so. Okay? And you've probably seen this before. Okay, adjacent to that angle is this leg, the hypotenuse of the right triangle is this, and the opposite leg to the angle is this one. Okay? And so often you'll hear people try to remember sine, cosine, and tangent using SOHCAHTOA. And that's what that says. Okay, the sine is opposite over hypotenuse, the cosine is adjacent over hypotenuse, and the tangent is opposite over adjacent. Okay? So if you ever want to check your memory, you can whisper SOHCAHTOA to yourself, and that'll remind you. Yes, sir? On the where now? Under period? Scribble. Zeros. I was trying to be all loopy. Okay? If you have questions about the zeros of this or about the zeros of the other two, just let me know, because I didn't write them down. I just said. Okay? All right. I'll say this, and then maybe I'll think about stuff. Okay. When theta isn't in the first quadrant, it's in one of the other quadrants. You can sort of use an extension of SOHCAHTOA, or you can relate the triangle back to the first quadrant and talk about it that way. But to be able to talk about theta inside each of these quadrants, you need to know what the signs of these trig functions are in each of these quadrants. Okay? And so some people like to remember them like this. So in quadrant 1, all these guys, all the trig functions are positive. In quadrant 2, only the sine is positive. In quadrant 3, only the tangent is positive. And in quadrant 4, only the cosine is positive. Okay? And you may want to remember this as cast, which I think is stupid because it's starting in quadrant 4. The one in the textbook says all students take calculus. Ali sings, teacher cries. Whatever you want, okay? Or you can just, use your head and see that, well, sine's positive up here, it's negative down here. Cos is positive over here, negative over here, and you can deduce tan from that. Okay? Okay. I'll use the giant seconds to just introduce these, and we'll do a couple of examples next time. These are called the reciprocal trig functions, the cosecant, the secant, the cotangent, defined like that. If you want, have a look at their graphs. Think about the domain and the range, think about their zeros, think about their asymptotes. Notice that cosecant is the reciprocal of sine, and secant is the reciprocal of cosine. It is possible to show these guys on the unit circle by various lengths over here. But again, these are just the definitions. Know them. If you want to look at their graphs, look at their graphs. All right, thank you, everybody. We'll do some examples now. I just want to do 2 examples, and then we'll go on to more trig. Example. Solve for x. Sine x is equal to minus root 2 over 2, or if you prefer, minus 1 over root 2. Okay? All right, unit circle. One. Okay, so sine is negative. So we're going to be down here somewhere. One possibility is that we're over here. Okay? And we recognize that from a special triangle, the minus 1 over root 2 thing. So if this is a unit circle, I'll put a 1 there. This is 1 over root 2. And this is minus, if you want, 1 over root 2. Okay? And from the special triangle this came from, you know that this angle is pi over 4. Okay? So one solution to this thing is minus pi over 4. Okay? And do I want to write, I'm going to change that x to theta. Okay? Okay, so one solution is minus pi over 4. Or if you like, you could go around this way and write 7 pi over 4. Okay? Does that make sense? Yeah.
It's minus pi by 4, so we'll subtract it by pi. Pi minus pi by 4.
You get 2 pi minus pi over 4. Yeah, you can go 2 pi minus pi over 4, which is 7 pi over 4. That also works.
Because sine minus theta is sine pi minus theta. Right?
Say that again.
Sine
mi-
minus theta
Yeah.
is equal to sine pi minus theta.
There's symmetries that I haven't talked about, so that might be one of them. Maybe.
So the answer would be 3 pi by 4, right?
No. So, okay, this is one answer, right? Obviously, because you can go this way and you get, here, I'll just write minus pi over 4 here. Minus pi over 4. Okay, that's obviously an answer, right? If I go minus pi over 4, then I get that, right? I get the sign is minus 1 over root 2. So that's obviously a solution. You could have gone the other way around and written 7 pi over 4. Okay? There are symmetries you can use, like those kinds of, if you have an identity that works, yeah, it'll give you a solution. Okay, so if you have some symmetry that you're sure works, that's fine. Another possibility, okay, again, sign was negative, so one possibility is here, another possibility is here. Okay. This is minus 1 over root 2, that's 1, that's minus 1 over root 2. Okay? And again, special triangle, this is pi over 4, this bit here. So the angle is pi plus pi over 4, or 5 pi over 4. Does that make sense? Okay. Are these the only solutions? No, because this thing's periodic, yeah? Okay, so the solutions are theta equals minus pi over 4 plus 2 pi n and an integer or 5 pi over 4 plus 2 pi n and an integer. Okay, and if you graph this thing and see where it crosses minus 1 over root 2, you should get the same result. Okay, yes? Divide everything by square root 2. Divide that by square root 2, you get 1. Divide that by square root 2, you get root 2. Does that make sense? Okay, give me a second. Okay, does that make sense? Okay, your job is to find solutions, all the solutions in a period, okay, and then extend to all periods. Does that make sense? Yeah.
Is it okay if you went from the same direction? So instead of from the negative and from the positive side?
Yeah, like 7 pi over 4.
Yeah.
So instead of this, you could write 7 pi over 4 plus 2 pi n, and that's fine too. Yeah? Just find 2 in a period. Yeah, let's say that, or 2 modulo a period. Okay? All right. Second example. Quadruple checking, people. Okay. Second example. If the cosine of theta is plus 3 over 5 and theta is between minus pi and 0, find tan theta. Okay? All right. I've been using unit circles so far. I'm going to show you one without a unit circle in case it makes your life easier. Okay, so just a circle. Okay. Theta between minus pi and 0 means down here somewhere. You want the cosine to be positive. Cosines are negative over here, so you have to be in here somewhere. Okay? Does that make sense? Okay, again. This thing told you, stay down here. and this thing told you, this plus sign told you, stay over here. So you wind up in this quadrant. Okay? All right. The cosine is 3 over 5. So 3 over 5. Okay, and again, I'm not using a unit circle here to show you how you can do it like this, okay? Okay, so when you use a not unit circle, the cosine is the x-coordinate over the radius, the sine is the y-coordinate over the radius, and the tan is y over x, okay? Or you can think of SOHCAHTOA with sines. That works too. Okay? So that's 3 over 5. Okay, Pythagoras tells us this is a 3, 4, 5 triangle, so this guy must be minus 4. Okay? So easy peasy. The tangent, actually, let me just say the theta was this thing. Okay, going this way, that's theta. Okay? And tan theta is minus 4 over 3. Okay? Or you can find the sine, or you can find the sine and then divide the sine by the cosine. Okay? Does that make sense? Are there any questions?
Can you explain again how did we get the minus sign?
This thing? Because it's down
Like the
here.
minus.
This guy?
Yeah.
Because it's down here. Because the y coordinate is negative because you're downstairs. That's it. Questions? Okay.